Today contains 35 cervical cancer risk factors for 858 women seen at a hospital in Caracas, Venezuela. This data was donated to the UCI Machine Learning Repository website, and the attributes cover a range of information including demographic, medical record, and various survey answers to questions evaluating sexual health. For this project, I'd like to be able to predict cervical cancer using the binary target variable called biopsy. Cervical cancer can go undetected for a long period of time if a woman does not receive routine screening. A biopsy is the most definitive way to identify the presence of cancerous cells on the cervix, so in order to improve detection in a data-driven way, I'd like to be able to build a classification model that determines which patients have cervical cancer based on the 35 attributes provided. To do this prediction, we'll create 3 models, evaluate the performance, and then determine if there's a way to string these models together using a stacked approach that might improve our accuracy. So let's take a quick look at the data and the number of members with cervical cancer. So there are 55 women with cervical cancer in this data set determined by a biopsy. And there are 3 other tests in here, Schiller, Heisman, and cytology, which I suspect are collinear because they are oftentimes performed together. So we should check this with the pairs.panel function, which I've already run here. It looks like the Schiller and Hinzelmann tests are in fact collinear with a correlation of 0.65. This means that positive test results tend to occur together for these 2 tests. This makes sense since during a colposcopy or Hinzelmann test, it's standard procedure to use staining or the Schiller test in order to identify areas of concern. So we will have to combine these 2 variables into, let's say, a variable called colposcopy. And here that's what we have done. Members with Hinzelmann or Schiller equal 1 will have colposcopy assigned to 1. So we should also look at the distributions for all of the rest of the variables. The first thing that you'll notice is that there are a lot of NAs in this data set. So we'll have to find a way to impute those. And there are also a couple of variables in here that are all zeros, so we'll remove those as well. First, I created a mode function that will calculate the mode of an input vector. Then I created an impute function that will use an if-else statement to impute the mode if the value is NA. Next, I created a variable for 5-year age groupings starting at 13 and ending with 43, which is past the childbearing age. So we use these age groupings to calculate the mode number of pregnancies within each age group, since I know that tends to change depending on age group, and then we impute them. And then next we calculate the mean number of, or age since first intercourse, and we'll apply that wherever there's an NA. And then we impute zeros for time since first diagnosis of an STD and last diagnosis. We also do the same for those who had NA for IUD, hormonal birth control, STD, and smoker variables. All of the maximum values are feasible in this data set as well, which I hadn't mentioned yet, so we will not be removing outliers. There don't appear to be unreasonable values outside of the expected ranges. So for a lot of these, the minimum values were 1, which implies that missing values might actually be people who have been diagnosed, who have not been diagnosed with an STD or used birth control or smoked, so it's appropriate to replace those with 0. Okay, and now we should look at the distribution of our continuous variables as well to check for normality. We have a few variables that look semi-normal, and then some that have a huge bucket of members in 0 and have a tail trailing off to the right. So let's see if we try to log transform at least hormonal birth control years, and it doesn't look like there was much of an improvement when we did that. So we'll leave the continuous variables as they are. In addition, we should see if any of these variables are linearly related with the outcome, and they aren't except for colposcopy, which makes sense since generally a colposcopy will come before a biopsy. So the next step is to determine our modeling approach. Given the binary endpoint, we'll explore a few binary classifiers. First, we'll look at a decision tree model. The data is well suited for a decision tree because they can handle large amounts of data with many columns and very transparent output. This method will help us learn a little bit about the variables and what features are most important in predicting the endpoint. The second model we'll test is a naive Bayes classifier, since the data has a large number of input variables that are mostly binary. And then I'd like to test the black box model, specifically neural networks, which I think would be a good route for this analysis and might pick up on more complex relationships among the data. So first we need to split the data into test and training. Since they aren't in any particular order, we can just take the first 70% for training and the rest for test. And we want to make sure that the biopsy results are distributed about the same in each. So 6% have cancer in the training and 7% in the testing, which is good. And now we'll train our decision tree model using C5.0. And we'll test it on the test data set. First, we should observe that the initial split is colposcopy, and then patients with a negative test result were classified as not having cervical cancer. For those with a positive result, there was another split on pregnancies, and then for patients with greater than 5 pregnancies, they were classified as not having cervical cancer. For patients with less than or equal to 5 pregnancies, there were 2 other splits on packs smoked per year and age of first sexual intercourse. So let's test the model on the holdout data, which we already did. There is a 96.1% accuracy, which is pretty good, and 3 of the test patients with cancer were misclassified as not having cancer, which is great. This model is already extremely accurate, so it's doubtful that boosting will improve our results at all, but let's just see what happens when we try to tune and test several parameters with tenfold cross-validation. We see that the best model with the fewest parameter inputs it has 1 trial, so increasing the number of trials and boosting doesn't really affect our accuracy at all, so we'll just stick with our original model. And then moving on to naive Bayes, we'll train using the same original training and testing sets, and then we'll test it on the test data. And the naive Bayes classifier is 81.8% accurate, which again is pretty good. This model might be less accurate overall, but did a better job at classifying true positives for cervical cancer. The downside is that there's an increase in the false positives, so 46 false positives total. So let's see if we can tune this model a bit more with the train function again. And I believe the best model that came out of this one in terms of accuracy was kernel equal 2 and Laplace estimator equals 0. So knowing that, we'll just print out the results instead since this is taking a while. Yep, there we go. Laplace estimator equals 0 and kernel equals 2 were the best in terms of accuracy. And we'll test whether or not the predictions were better. And it looks like we didn't really predict any of the cancer patients well. So we'll move on and use our original neural or naive Bayes that we predicted earlier. Moving on to neural network, we have to normalize the data before we train the neural network. Since most of the variables are binary, we can scale everything on a scale of 0 to 1. So let's do that. Okay, great, that worked just fine. And then we will train without a few of the variables because they are mostly 0 for the testing set, so we remove those. And then on our test data set, we'll see how the holdout performed. Okay, so the model is 91.5% accurate. 12 patients with cancer were not classified as having cancer. Um, let's validate this and see what happens when we test several values for hidden nodes and the decay parameter. I think we already ran this. Let's skip the running of this and see how it performed. Okay. So when we tune this perfectly, the optimal size is a hidden network of 1 and decay of 0.1, and the performance is 100% accurate, which is very impressive. So moving on to our rating of these models in terms of accuracy. The measure of accuracy is AUC, and we also plotted ROC curves with a reference line for a model that is totally unable to differentiate the members with and without cancer. AUC near 1 is perfect, and we prefer models in the upper left-hand corner of the ROC graph. So when we run this and compare, we see that the neural net has perfect prediction. The naive Bayes is alright at predicting the endpoint, and the tree model is a little bit better than naive Bayes, and that is reflected in the ROCs as well. Naive Bayes at 89.8% AUC, and 90.3 for the tree model, and 100% for the neural net. Okay. Let's move on to an ensemble learner. We can experiment with bagging on the tree model, which doesn't really improve our accuracy at all. When we ran bagging, 95.3% accurate, and we predicted correctly 14 out of the 21 cancer patients. So let's just stick with our original model for the tree without bagging. When we ran this on the neural network, we didn't see any improvement in accuracy in terms of predicting the actual cancer patients. So again, we'll just skip bagging for the naive Bayes as well. Even though it had improved accuracy, it didn't do a good job of predicting true positives. So we'll just use our original naive Bayes result. Okay. So we want this ensemble to be as generalizable as possible. Let's see if stacking the models will provide a less biased and still accurate prediction. Since we still haven't really touched regression, let's try using logistic regression as our meta classifier. Since logistic regression will be a little bit boring, if one of the models is 100% accurate, I'll use our initial neural net result, which is a little bit less accurate in the stacked model. With the stacked model, we've achieved, let's see, I believe it's 95% accuracy overall. Yep, and we predicted correctly 14 of the cancer patients. Okay, so even though we had some instances where the individual models outperformed the stacked model across the board in terms of overall accuracy, true positives and true negatives, it's important to remember that the stacked models are much less prone to bias, and it's more generalizable than any one of these models alone. Additionally, each of these models recognizes unique and subtle patterns within the data that we surely would not have captured when applying these just alone to the broader population. It's suspicious that the models were so accurate, and this makes me a little bit skeptical that the models can truly be generalized and predict new observations. If we were to repeat the analysis, I'd probably use a randomly selected 400 from the original training set to train, and then the rest of the 258 hold out for our stacked model. Given the caveat that it's such a small sample size and the endpoint is rare, I believe we did the best that we could with this method here, and it would be ideal to have a larger number of observations in order to avoid these potential overfitting issues.